All right, we're back. We're on page 70 of math analysis. We're talking about trig identities, and we're talking about the fundamental identities. So there's 8 fundamental identities, and you get 3 types. There's the reciprocal identities, of which there are 3, and they are by definition. So cosecant is going to be 1 over sine, or sine is 1 over cosecant. It doesn't really matter. Secant is 1 over cosine, or cosine is 1 over secant. And cotangent is 1 over tangent, or tangent is 1 over cotangent. Depends on how you're using them, right? But 3 reciprocal identities. We also get 2 ratio identities. Ratio identities are ratios of trig functions, basically. So tangent is sine over cosine, by far the most famous of them. And then cotangent is cosine over sine. We went through and we showed why those are true in a couple of different ways, I guess. And now what we're going to do is we are going to talk about the Pythagorean identities. These are a big deal, like a really big deal. So this, so-called because they basically follow the Pythagorean theorem, and we'll like kind of see that in a second. But they are sine squared plus cosine squared equals 1, which is like the king of all of them. The one identity to rule them all, I guess. So you definitely need to know this one like forever. Now, the other ones are a little less common, but common. We're going to use them all the time. Tan squared plus 1 equals secant squared. For sure that is going to be true. And then 1 plus cotan squared equals cosecant squared, which if you look at it is really similar, right? We got tangent, and then it's cofunction, not its cofunction. Tangent there and secant there. They're not cofunctions. But then here we have the cofunction of tangent, the cofunction of secant. So it's a very similar identity. And then, you know, you gotta memorize those. The tangent secant one does come up quite a bit. The cotan cosecant one, I would say, is definitely less common, but you'll see as we do them, I guess. So we want to show that sine squared plus cosine squared equals 1 by just kind of connecting things in about the unit circle. So sure, if we think about the unit circle, let's get that. I don't know if that's actually a vertical line. It looks pretty good, I guess. And a circle, which also, okay, I think that's good. And what we need is a point. So I'm gonna put a point here, I guess. And then this point is definitely cosine theta, sine theta. But then it's the unit circle, right? So what's the equation of the unit circle? It's x squared plus y squared equals 1. So what's going to happen if I substitute, right? X equals cosine, y equals sine. So, I mean, just based on that, therefore, cosine squared plus sine squared. I don't know if we really talked about where you put the exponent with trig functions. It's in kind of a weird place, right? You put it before the variable so that you don't run into the ambiguity of like, what do I mean by cosine of theta squared, right? Do I mean square theta, which is such a bizarre thing to do, but do I mean square theta and then take cosine, or do I mean take the cosine and then square it? So what we do is we put it right after the trig function before the argument of the trig function. It's just less confusing that way. There's other ways we could prove this. Like if we wanted to, we could have said that, you know, sine of theta, do a right triangle type thing. Sine of theta is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. And so then if I square them and add them up, like the key thing here is like, you'd have to think like, well, what if I squared them and added them? So I mean, I'm going to do that. So then sine squared of theta plus cosine squared of theta will equal the quantity opposite over hypotenuse squared, and then adjacent over hypotenuse squared. And then if I actually do that, I would get opposite squared plus adjacent squared over the hypotenuse squared. But then you got to think of your triangle. Why am I squeezing this in? You got to think of your triangle now, right? And in the triangle, we know that, let me get here, That's the sum of the legs of the triangle, right? Why? Okay, let's go one more. Nope, nope. Okay, we're gonna have a bad triangle. There, how's that for your auto shapes? Right, we have opposite, adjacent, uh, hypotenuse. So hypotenuse squared is, so that opposite squared plus adjacent squared is hypotenuse squared. This is taking a really long time for something that's not actually in the notes. So we get hypotenuse, oh my God, hypotenuse squared over hypotenuse squared, but that's just one. So then we have sine squared plus cosine squared. I'm not sure which way is the more famous. It's probably sine squared plus cosine squared, but it should be cosine squared plus sine squared because of the way the unit circle is. But you know, cosine always loses out. Like it should have gone first, never does. It's the co-function, you know, it's like there's a lot going on there. All right, let's try these. So solve or evaluate each of the following. So so now you're getting to the point. In general, if you see sine squared and cosine squared, you probably want them together, and you probably hope that somehow they're being added and just equal 1. So let's see if that happens here. So I get sine squared of 53 pi over 9 plus cosine squared of 53 pi over 9. And then I'm going to say that that equals 5 minus 2x. Move everything that's not a trig function to one side. So we get this. Now here's the deal. If this and this are the same, then that's going to equal 1. So this whole thing actually is just 1. It's like weird, and that's going to start happening all over the place. Like you're going to see a lot. Subtract 5, you get negative 4. Divide by negative 2, you get 2. So x equals 2. Which is weird, right? And once you get used to it, not that bad, but you know, you got to get used to it. Now here we see sine squared plus sine squared. That's going to be a problem unless we can turn one of these into a cosine. And it doesn't really matter which one you choose. Well, maybe it does. It doesn't matter in terms of the answer. It might matter in terms of how much work you need to do. So what I'm going to do is I'm going to turn this one, I think. So I'm going to change this into cosine. The reason I'm going to do this one is because the denominator is only 7, and to change it, I have to do cosine of pi over 2 minus that, and then the common denominator will be 14, so I feel like it has the best chance of like simplifying quickly. I'm going to say sine of 11 pi over 7 is equal to the cosine of pi over 2 minus 11 pi over 7, all right? Which is equal to the cosine of, that's 7 minus 22. 7 minus 22 is negative 15 pi over 14. But cosine's an even function. So since cosine's even, the cosine of negative 15 pi over 14 is the same as the cosine of 15 pi over 14. So let's maybe annotate this, I guess. This is by cofunction. And then this is because of even function. So we got a lot going on there. Now, why is this helpful? Well, that means that this problem that we're doing is the quantity. So I didn't even look at that, the fifth part. That would be bad if this was anything other than 1. And you kind of like, as you do problems like this, you start to feel like, oh, that's probably 1 because nobody would really expect me to do something to the 5th power, to the 5th. But this whole thing, that was the whole point of doing it. This whole thing here is just 1. So this is going to be 1 to the 5th, which is 1. Not bad at all. But you got to get used to it, right? So sine squared of theta plus cosine squared of the same theta equals 1. You use it all the time. The other one's tan squared plus 1 equals secant squared. I always say that tangent and secant are like secretly dating. When one of them comes up, the other one is just going to be there. Like they travel in the same circle all the time. And then 1 plus cotan squared equals cosecant squared. I honestly have to think back to the tangent one all the time to really remember the cotangent one. But that's okay, because you know, you come up with ways you're going to remember things. So what I'm going to do, I think, is stop this video here, come back in the next video and finish off this page. Who knows? We'll see. So I'll see you there.